Hey everyone, in this video we're going to be doing some statistics practice, specifically with skills that might show up on the AP Biology exam or in your AP Biology course. Now all of these will fall under AP Biology Science Practice 5, Statistical Tests and Data Analysis, so hopefully this will be helpful for you in your exam review or in your course. One of the very simple skills that you should be able to do in AP Biology is to calculate a mean. Remember, the mean is just the sum of all data points divided by the total number of data points. When you're calculating things in AP Biology, a lot of times it'll tell you to calculate to a certain decimal place. So for example, here to the nearest tenth. So make sure you pay attention to that and try not to round to the very end of your calculations. In this particular problem, a student collected the following data in an experiment measuring the height in centimeters of Arabidopsis plants over a 2-week period. Now we need to calculate the mean to the nearest tenth. Here are all the data points, and if you want to pause the video and calculate the mean on your own, go ahead. But what we're going to do is sum all these points up and then divide by the total number of data points, which in this case is 10, and that should give us 7.3. Now again, we've rounded to the nearest tenth because that's what the problem is asking us. You should also be able to calculate a rate in AP Biology. Now this includes some of your population math, but in general just reaction rates as well. On our formula sheet, we have the equation for rate, which is dy over dt, dy meaning the amount of change, dt the amount of change in time. Sometimes this can be interpreted from a graph in AP Biology, but you can basically just use the slope formula. So on a graph, we could calculate the slope at different intervals of time. So let's take a look at this data set in this graph. Here we're looking at the rate of reaction of enzyme Y, a pretend enzyme for the sake of this problem. The activity of enzyme Y can be measured by the concentration of its product. So in this case, molecule Z is what's produced during the reaction. So in this experiment, every 10 minutes, the molar concentration of molecule Z is measured. Then it's graphed, or you might have to graph it yourself on the AP Bio exam, and we can see that in the graph here. So then we might be asked to calculate the rate of this reaction in a particular time period. So let's say we've graphed our data, now we want to calculate the rate of the reaction from time period 0 to 30 minutes. So let's start by looking at our time period. It's starting at 0 and going all the way up to 30 minutes. And then we're looking at the change in molar concentration. So that starts at 0 as well, and that goes all the way up to 15.4 micromolar. So we would set this up by first looking at the molar concentration for our y values here. Again, that's graphed on the y-axis. And again, we're looking at the rate, so dy over change in time dt. So we'll look at time in a moment. So we'll set this up by using amount 2, so that's 15.4, minus amount 1, which is 0 here. And those are going to be our y values in our slope equation. Remember to include the units if you're writing out how you would set this formula up on the AP Bio exam. Now we're going to look at our dt, or our values for x. Remember, we take the second value first, which is 30 minutes, subtract our first value, which is 0, so 30 minus 0. So now we have 15.4 micromolar minus 0 micromolar divided by 30 minutes minus 0 minutes. Now in this problem, I didn't ask you to round to a particular place, so we're going to go ahead and do it to the nearest hundredth. But when we perform this equation, we would get a rate of 0.51 micromolar per minute. Do not forget the units when you're calculating rate. Another skill that you'll need to know is how to calculate a ratio. This one is another pretty simple calculation, but you're just comparing one data point to another data point, so you're dividing data point A by data point B. So we would see this maybe in a situation where we're looking at surface area to volume ratio and comparing which cell might be more efficient in exchanging materials or removing waste by diffusion. So if we just look at these two cells, what we want to do is see which one has the greatest surface area to volume ratio, and that'll be the cell that is more efficient. So you do have the equations for surface area and volume provided to you on the formula sheet for AP Bio. In this case, it's already given the surface area and volume, so you don't have to calculate those separately. But to calculate the rate, we just divide our first value by our second value, value A by value B. So in this case, that's 600 divided by 1,000 to give us 0.6. And then for our cell B, that's 5,400 divided by 27,000 to give us 0.2. In this case, cell A has the greater surface area to volume ratio, and so it is more efficient at exchanging materials. Another skill that you might need to be able to do is calculate percent change. This is especially useful in an experiment where we're using different individuals or different organisms and trying to see how much they've changed in a particular experimental setup. For example, we have 2 mice in this experiment, and we want to see which one had the greatest percent change or the greatest percent weight gain in the experiment. It wouldn't be good just to look at their final weight because we know that they're starting at different weights. From week 1 to week 5, which mouse had the greatest percent weight gain? So let's just look at percent change for mouse A. What we want to do is take our final weight and subtract our original weight. So we have 19 grams minus 11 grams, and then we're going to divide that by 11 grams, our original weight. That'll give us a decimal of 0.72. And again, I'm going to round to the hundredths place for this particular problem. We want to get a percentage because we're looking at percent change. So we're going to then multiply this by 100 to get our percent. So this mouse had a 72% change in weight over this period of time. Let's compare that to mouse B. What we'll do here is just subtract 13 from 21 and then divide by 13. And that gives us 0.62. We multiply by 100 and we get 62% change in weight. Another important skill is being able to both draw and interpret error bars. We're not going to do any graphing in this particular video, but I do want you to practice reading a graph with error bars. If we're looking at this experiment, we have different individuals that have different levels of participations in sports. Some participate rarely or never, some participate once in a fortnight, some participate once a week, and some participate more than weekly. And then the experimenters measured their resting pulse rate and took the means of each of those groups. Now, if you look at this graph, it may look a little weird because you don't see any actual bars, but technically this is a bar graph. This is one way that bar graphs can be drawn, with just that dot or circle as the top of that bar, and then the error bars are there. You may see a graph like this, or you can graph like this as well on the AP Biology exam, but just imagine the bars are there if you do not see them. We can also see error bars on line graphs as well, so don't get thrown if you see an error bar or if you're asked to graph error bars on line graphs too. So looking at this graph, we want to determine if there's overlap between any of the bars of our sample mean. Most of the time in AP Biology, these will be calculated for a 2 SEM value, which means there's only a 5% chance that the true value is not within the span of those error bars. So let's look at this question here. Which levels of participation in sports had statistically different mean resting pulse rates? So let's take a look at each of these examples. Let's compare the rarely and once a fortnight group first. We look at the span of these error bars. We want to see if there's any overlap between the rarely group and the once in a fortnight group. So this is the span of the error bars for the rarely group, and we can see that there is overlap between rarely or never and once in a fortnight. So they did not have statistically different mean resting pulse rates. If we compare once in a fortnight and once a week, we can see that there also is overlap between these two groups as well. So they did not have statistically different mean resting pulse rates either. Now let's compare rarely and more than weekly. So in the rarely group, we can see that the error bars span a pretty good amount, but there is no overlap between the error bars of this category and the error bar of this category. So because there is no overlap, this means that the sample means are statistically different in this particular experiment. So that would be the answer we choose for this question. Now, included in Science Practice 5, you also want to make sure that you are able to correctly use and interpret the Hardy-Weinberg equations, as well as calculate chi-square values, interpret p-values for a particular data set, and know how to accept or reject null hypotheses. I'm not going to go into those skills in this video, but I do have other videos which I'll link in the description below if you want to practice those skills as well. Make sure to give this video a like if it's been helpful. Good luck with your studying, and I'll see you later.